Hello everybody and welcome back to more of the 2001 Euclid paper. We're on to question number 4. Let's have a look at that. So we've got question number 4 here, and we've got two parts, A and B. A is a light bulb and B is written. And A says if f of t equals sine of, and then in brackets we have pi times t minus pi by 2, what is the smallest positive value of t at which f of t attains its minimum? Okay. So f of t is basically just a jazzed up sine function. You know, we have the sort of period stretched out a little bit. The function itself is shifted a little bit on the t-axis. But essentially this is just going to be the sine function. So we have the same maximum, the same minimum we usually do for the sine function. So the minimum value should be minus 1. So now the question is, what's the smallest positive value of t at which this function here becomes minus 1? Well, we have to stop and think, when is sine minus 1? Okay? Well, I always like to remember it by just sort of drawing a sine function out. So the sine function starts at 0 and then achieves its peak at 1 at pi by 2. Then it plunges, and then at pi it becomes 0 again. And then at 3 pi by 2, we're down at minus 1. And it just continues on and on like this. Okay? So there's 2 pi there, and so what is it? It's 5 pi by 2. No, here's 5 pi by 2. 7 pi by 2. Right. Yeah, sorry, this is 3 pi, not 2 pi. My mistake. 2 pi is over here. Okay. So sine of x achieves its minimum. It's minimum of minus 1. Whenever x is, and then we have to be careful here, whenever it's 2 pi, so with 2 pi minus half a pi, we get back here, and then we'd have 4 pi minus a half pi to get back here. So 2 pi, I guess, k here. Where k is an integer. Okay? That's when we're going to get a minimum here. And although I didn't plan it, if you look, our expression here for when we get our minimum of minus 1, that looks very similar to our expression pi t minus half a pi. Didn't plan that, it just happened to work out that way, the way I was writing out the minus 1s there. So, we want the smallest positive value of t. So that pi t minus pi by 2 looks like 2 pi times k minus pi by 2. Well, these pi by 2s are going to cancel out. And then the resulting pi's we can divide through by them. So what we want is t to look like 2k. So we want t to be a positive even integer. So to be a positive even integer, and the smallest one of those is t equals 2. Okay, and we can check pi times 2 minus half a pi is going to be 3 pi by 2, and that is actually the first time it becomes minus 1. Okay, so we've satisfied exactly what we needed to do, and this has got to be the smallest value of t that works, because there is no smaller positive even integer. Okay, so that was A part. Not too shabby. We just had to sort of remember the nature of the sine function. And now we have the B part. So in the diagram, angle ABF is 41 degrees, and angle CBF is 59 degrees. So together those add up to an angle of 100 degrees. I don't know if that'll be useful yet, but our full angle here at B is 100 degrees. Okay. DE is parallel to BF. Okay, we can see that from the little sort of arrow they have here. And EF is 25, just as they have it labeled. If AE, so the distance from A to E, is equal to EC, determine the length of AE to 2 decimal places. Okay, so I suspect we're going to be rounding. And I also suspect, just based on the fact that we had sines in the previous question, that we might be needing to use some trigonometry. I noticed my diagram has a lot of right angle triangles. Right angle triangles and given angles are often associated to trigonometry. So we might start thinking sine law, cosine law. It might not turn out that way, but that's the sort of thing we should probably be thinking about. Okay? So, in order to get a better sense of the question, and maybe add in some information. Like I noticed these parallel lines will give me the angle at D. It'll also be 59 degrees. We might try to redraw the picture in our notebook. So let's do that now. I'm going to draw a bigger picture, so I'm going to get another piece of paper. So we have 25 here, E was down here, C, A, F, B is over here, D is over here. These two guys are parallel. We got right angles here, and we're told that this is 41 degrees and that this one here is 59 degrees. For a grand total, as I mentioned before, of 100 degrees. And we can start to fill some things in. For example, we know that the interior angles of a triangle are going to add up to 180 degrees. Well, we have angle at A plus angle at B plus angle at F. We should get angle at A is 49 degrees. Okay. Other things we know, because we have DE and BF are parallel and they strike the same line BC, then their angle of incidence is going to be the same. So this guy here is going to be 59 degrees as well. And once we know that the angles in a line add up to 180 degrees. So 59 plus this angle here is going to have to be 180 degrees. So we're going to have 121 degrees here. Okay. Other things that we can do, we can let EC is X, and we'll let AE be X. So that tells me that AF is X minus 25. So I don't know which of these things are going to be needed, but we have them included just in case. Okay, and I think that's just about all the information we were really given in the problem. We want to determine the length of AE, which we've called X, to 2 decimal places. So ultimately, that's what we're trying to get is X to 2 decimal places. Okay. So now the question is, how do we go about getting that? I guess I can also give the angle at C there. That's going to be 31 degrees, so that's probably useful. Because DEC is a triangle, so the sum of the angles there needs to be 180 degrees. 59 degrees plus the 90 at E plus 31 degrees at C gives us 180, like we needed. Okay. So one other thing I'm noticing here is, so let's make our observations here. Just by looking at the angles, it's clear that triangle CDE and triangle CBF are similar. Okay. What else can we do here? So what I sort of want to do is maybe compute BF in two different ways using some trigonometry. And that should be, we compute BF in two different ways using X, and I think that might get us a solution. What else is there that we could possibly do? I think that should really be it. I think with the angles that we have, we're all set. So, let's see here. So I'm remembering my SOHCAHTOA. So sine is opposite over adjacent, or sorry, sine is opposite over hypotenuse. Cosine is opposite over hypotenuse, and the tangent is the opposite over adjacent. So if I know the angle CE here, or sorry, if I know length CE, which I've called X, and I know this angle is 31 degrees, I know that DE, which is the opposite angle, over CE, is the same as tangent of 31 degrees. By the exact same reasoning, I know that x minus 25, which is AF, and so BF is opposite there, so BF over AF is going to be equal to the tangent of 49 degrees. Okay? So there I have BF right there. And once I know DE, so since CDE is similar to CBF, then I know that the ratio between BF and DE, because they correspond to one another, is got to be the same, or has got to be the same as FC over EC. Okay, but that's the same as x plus 25 over x. Okay. So this last statement, BF, is the same as DE, or not D, yeah, DE, times x plus 25 over x. Okay? But if I rearrange these two statements up here, I know that DE is the same as CE times tangent of 31, but CE is just x. So we get x times the tangent of 31. Similarly, I know AF is x minus 25. So BF, my sort of common side length, is AF, which is x minus 25 times tan 49. Okay. So here, substituting in, BF is x tan 31, x plus 25 over x, and these x's here are going to cancel out. And now I have two different expressions involving x and known numbers. So 2 different expressions involving x and known numbers for BF. So I can set them equal. So x minus 25 times the tangent of 49 has to be the same as x plus 25 times the tangent of 31. Right, it was the tangent of 31, right? Yeah, tangent of 31. Okay. Well, x, if you recall, is the number we want. So let's expand some of this out. So x tan 49 minus 25 tan 49 has got to be equal to x tan 31 plus 25 tan 31. X, and then we have tan 49 over here, and we can bring the x tan 31 across. So tan 31. And we can bring the 25 tan 49 to the other side. Plus tan 31. So x, if we divide through by tan 49 minus tan 31, x is equal to 25 tan 49 plus tan 31 degrees all over tan 49 minus tan 31 degrees. And now I have an expression, although admittedly not a particularly nice one, but I have an expression for x, and x was what I wanted to solve for. So we grab out our calculators, and we just do a little math. I just need to double check. Yeah, I'm in degrees here. So tan 49 plus tan 31 is equal to about 1.75. So we times it by 25, and I divide by tan of 49 minus tan of 31. And I get 79.6726 and so on. So I just add that in. Just use my calculator. It's a good reason to have calculators. I don't think you can get this one. Anything that really says to decimals to 2 places, you probably should have brought your calculator for. So here we have 79.6726. So we're just going to round that out to 79.67. We were asked 2 decimal places, so there we go. So it's 2 decimal places, x equals 79.67. Okay. Now, with that number at the end, there's no real check we can do to make sure we got everything nice and quick and correct. We could probably, then compute BF and DE, but none of these would really allow us to check whether or not we got the right answer. So if we wanted to come back and check, really the only thing we could do is just run through our reasoning with our tangents, our sines, our SOHCAHTOAs, and see if we were right that way. And that does it for question number 4. It's a nice little question, but they're only going to get harder from here. And in the next video, we're going to take a look at A and B for question number 5. So I'll see you guys then.